Hey everybody, welcome to 2.6. Today we are going to look at complex roots. That would be roots that have real parts and imaginary parts. So before we do this, you will need a calculator or a calculator app. The calculator app on your Chromebook is fine. Desmos calculator on any device that connects to the internet is fine. Let's look at this little review here. Parent functions. Y equals x has a single root. It goes clean through the x-axis. And it does go through 0, 0. Let me adjust this real quick. Over adjusted. All right, there is y equals x. Single root goes clean through the x-axis. No bouncing or zigging. Y equals x squared is a perfect parabola. Vertex at 0, 0. A double root will have a tangent bounce. Tangent meaning it touches but does not go through. There's an N in that word that I forgot. Okay. Then y equals x to the third. That's the one that looks a little funny. It zigzags. So it's going to come up really close to the the origin, and then zig through. Okay, so that the triple root, remember, makes a zigzag shape. Okay, now we want to draw a situation, draw graphs for each of these situations. Two single solutions would go through the x-axis twice, two different locations. So we could have something like a parabola would make two single solutions. Now, two double solutions in the next one and nothing else, we would have to hit the x-axis, bounce off of it, then hit the x-axis again and bounce off of it. And that would give us our two tangent bounce roots. A triple solution would look something like this, going through the x-axis at a zigzag. One pair of non-real solutions. Non-real solutions always come in pairs, and this will be something that could not cross the x-axis. So we would have something like a downwards facing parabola, never crosses the x-axis. Okay, now this last one gets a little fun. Two double and one single. So if we have a double, we bounce off the x-axis. I'm going to put a single here, go through the x-axis, and then I'm going to bounce off the x-axis again. It's not the only option for any of these graphs. There's multiple graphs you could draw for each of these. Key thing to remember, a double root is a tangent bounce, and a single root goes straight through the axis. Then a triple root does the zigzag thing. So let's look at the degree of each of these polynomials. A has two single solutions. It's a degree of 2. B has two double solutions. That's 2 and 2 more. So that's a degree of 4. C is one triple solution. The triple solution counts 3 times. So that's a 3. D has a pair of non-real solutions. That is a degree of 2. Even though the solutions are not real, it is a pair of solutions, so it counts as a second degree. E has 2 double and 1 single. That makes a degree of 5. 2 for each double plus 1 for the single. Now, let's take a look at example 2. We have this polynomial. Y equals, or f of x equals x to the third minus x squared plus 9x minus 9. It is a degree of 3. It's a degree of 3, so we are expecting 3 solutions. Okay? Now, we want the real root that can be found by graphing this. So, going to the calculator, I already have this in. We have a root. Okay, we do have one real root where this crosses the x-axis. So in y1, I have the equation as it was given to us. In y2, I have equals 0. That's what's causing that red line on the x-axis. That way I can do my intersections as needed. Now, this root that we can see here looks to be at 1, x equals 1. I'm going to go to the table. I'm going to go down to x equals 1, and sure enough, there is a 0. At 1 comma 0, there is a root. So x equals 1 is a solution. Now, back to the graph here real quick. There are no other solutions. We can keep zooming out, but it will still give us just that one solution. So let's talk about what's going on with those other solutions. The one real root solution we have is x equals 1. That means x minus 1 is a factor. Okay? Now, we can't see those other roots. Those other roots are imaginary. Not real. They involve eyes. Okay? So, this graph almost looked linear. Sort of. It's really poor imitation of that graph. I apologize. So this one root here at 1 is all we have. Okay? Now, what we do from here is we want to divide out that factor of x minus 1. So to divide that out, we'll use synthetic division. So from the original function, no powers were skipped. 1, negative 1, 9, negative 9. We're dividing by x minus 1, so we put a positive 1 on the outside. Bring down your first coefficient, it's a 1. Multiply, we get 1. Add, we get 0. Multiply, we get 0. Add, we get 9. Multiply, we get 9. Add, we get 0. Now, that 0, remember, is the remainder. We're not really surprised that's a remainder because we know from here that x minus 1 is a factor because x equals 1 is a root. So we were expecting that 0. Then that 9 is the constant, the 0 is the x coefficient, 1 is the x squared coefficient. So when we divide this out, the result we get is x squared plus 9. Now, that multiplied by the x minus 1 is equivalent to the original f of x. This f of x equation and this f of x equation are the same graph. It's like saying 10 is the same thing as 5 times 2. It is. We factored it. Okay? Now, what we want to do from here, once we get this other factor, is we want to be able to solve and find those other solutions. So, we'll take this x squared minus 9 factor, x squared plus 9, set it equal to 0 to solve it. There's only one term of x here, so isolate that x. X squared would equal negative 9. And then to solve that, we would need to take the square root of both sides. Well, that's a square root with a negative number. So what we need to do is factor out that square root of negative 1. So negative 1 times square root of negative 1 times square root of negative 9. So here, x equals that negative 1 is an I. Square root of 9 is 3. And since we took a square root, there is a plus minus sign here. So our solution here is plus or minus 3i. I for the imaginary, 3 for the square root of 9. So plus minus 3i is the solution to that second factor, the x squared plus 9 factor. Now, all of the solutions, okay, we said right up above this that we had 3 solutions. So all 3 of those solutions, x equals, we had 1 that we could see on the graph, and then we found the other solutions, plus or minus 3i. Now, that plus or minus 3i is not going to show up on the graph. It is imaginary. It's not going to show up on the graph. Okay. Now, 3 solutions. 3 solutions. Found 1 on the graph. Used synthetic division to divide that factor out. Solved what we had after that. Now, let's look at example 3. Okay, let's look at example 3. 6x to the third minus 35x squared minus 52x plus 21 equals 0. That is a third degree polynomial, so we should have 3 solutions. 3 solutions. So, going to the calculator, going to y equals, putting that equation in. Or turning the other one off and turning this one on. Okay, so there is our equation. When we go to graph this, we see 3 solutions. We see 3 solutions. Okay, now, only one of those solutions is at a nice number. So if we go to the table, we can figure that out. Okay, and I'm looking at the Y3 column here now. So when we go to the table, I'm going the wrong way. Sorry. When we go to the table, we're looking for that Y value of 0, and we see that that happens at x equals 7. We see that happens at x equals 7. So at x equals 7, we have a root. So the only nice root is over here at x equals 7. Okay, we do have 3 real roots. We could see all 3 of them on the graph, but the only nice solution is at x equals 7. So we want to use synthetic division to divide out that factor and find the rest of the equation in factored form. So no powers are skipped. So 6, negative 35, negative 52, positive 21. We're dividing out that root of 7. So that means x minus 7 is one of the factors. So we'll have a 7 on the outside. Bring down the 6. Times 7 is 42. Add, we get 7. Multiply, 49. Add, we get negative 3. Multiply, negative 21. Add, we get 0. Now, we're not surprised we got 0 because we knew we had a root at x equals 7. Okay, now the shape of this graph looks something like this. Now I'm probably have to draw over that later, but that's okay. Now, what we have is a remainder of 0, constant of negative 3, x coefficient of 7, x squared coefficient of 6. So our polynomial now is 6x squared plus 7x minus 3. Okay? Now, what that means is that we can solve that quadratic. Now, we want to see if it will factor some more first. So we look for sum and product to see if this will factor any more. Might not. If it will factor, factoring it will be simpler than solving it with quadratic formula. Okay, so I'm going to take this quadratic, 6x squared plus 7x minus 3 equal to 0. If this will factor, we need a product of negative 18 and a sum of 7. Well, 2 times 9 is 18. Putting a negative on the 2 gives us the signs we need. So this will actually factor. So 6x squared minus 2x plus 9x minus 3 is equal to 0. Group and greatest common factor. So first factor, greatest common, would be 2x. Divide that out, and we get 3x minus 1. That second factor would be plus 3. Divide that out, we get 3x minus 1. So we have the factors of this polynomial, okay? The total factored form would be f of x equals, the first factor was that x minus 7, times the 2x plus 3 we just found, times 3x minus 1. Now, to solve these, we already know we had a solution at x equals 7. Take 2x plus 3, set it equal to 0. 2x equals negative 3. X is negative 3 over 2. Take 3x minus 1. I have to do that up here. Set it equal to 0. 3x will equal 1. X will equal 1/3. And we already knew that x equals 7. So our three solutions here, x equals, they're really hard to draw, curvy braces, negative 3 over 2, 1/3, and 7. And those are the three solutions. So use the calculator to find the first whole number solution. Use synthetic division to divide that out. And then try to factor what remains. If what remains won't factor, then you can use quadratic formula. Or you can go to quadratic formula anyway. It works on any quadratic, whether it factors or not. So, let's try another one. Let's look at example 4. X to the 5th plus 5x to the 4th minus 2x to the 3rd minus 4x squared. If we go to the calculator, I already have this in the calculator, so I'm going to turn off the previous one and turn this one on. Why do I feel like something's missing in that equation? Maybe not. Nope, we're good. So when we go to graph this equation, we see lots of curves. We see lots and lots of curves, especially really close to that x-axis. Really close to the y-axis, I'm sorry. Really close to the middle there. So what we can do is we can use the calculator to find those solutions. We can go to the table, see if we get any real number solutions. I'm looking for zeros in that y4 column now. Okay, oh, I see 2 right here. At 1 and at 0, we have solutions. At 1 and at 0, we have solutions. So there's 2 of those roots. If we go back some more, it doesn't look like I can find the other root. I switch from positive to negative y's here. Okay, and there's not a 0, there's not a whole number root where that's going to happen. Okay, so we do know that we have 2 of those roots. Okay, we have 2 of the 4. We see that x-axis being intersected 4 different times. So we have a root at 0. We had a root at 1. Okay, if we look at that picture again, okay, we had another root a little bit negative and another root a lot more negative. So we've got a root a little negative and a root a little more negative. Now, the other thing to notice that's going on is that really close at 0, I'm going to zoom in. I'm going to zoom in and zoom in. When you zoom in on your calculators, you have to hit zoom in and then hit enter for it to work. So you see at x equals 0, we have a bounce. We have a tangent to the x-axis. That tangent bounce tells us we have a double root. So, looking at this, our graph bounced at 0 and basically did this. Okay? So, the total number of zeros in this polynomial needs to be 5 because of the degree of 5. We have a single root. We have a single root. We have a double root, which counts as 2. And we have a single root. So that does add up to 5 roots. We have 3 single zeros. We have 1 double that counts as 2. We have no triples. And this already adds up to the 5 roots we need, so there's no imaginary. Okay? We already had 5 roots with these singles and doubles. So C, D, E, and F add up to 5 roots. Okay? Now, what we need to do here is find those other roots, the 2 on the left. Those are the not so nice ones that we don't have yet. If we look at the calculator, we can make the calculator find them. Second trace, intersect, you hit enter, enter, and then move your arrow keys before you hit the third enter. Okay, so this gives me an intersection, but that decimal, negative 0.6393, that's not a nice decimal. Okay, that's not going to turn into a nice fraction for us. If we try the other one, furthest left, second trace, intersect, enter, enter, and then scroll closest to this far left root before you hit the third enter. We get another really, really yucky decimal, negative 5.23607. That's not going to be a nice fraction. Okay, so this is where we are going to need some other solving methods. Okay, we do have 2 solutions, a double and a single, that were pretty numbers. So we're going to use those first and then divide those out. Okay, first thing I want to do here is looking at this function, I want to factor out that x squared. Okay, every term has a factor of x squared. If we factor that out, x to the third plus 5x squared minus 2x minus 4 is the other factor. Okay, so that will help us as we start doing this synthetic division. Okay, now I'm going to go ahead and put factored form here. F of x equals x squared. And then we're going to do synthetic division to find those other factors. Okay, we know that we have a root at x equals 0 and that it is a double. That's the x squared factor we already factored out. We also know we have a root at x equals 1, and that was a single root. We need to factor out that root. So we'll go to synthetic division. We'll go to synthetic division, and we'll use our coefficients. 1, 5, negative 2, negative 4. 1, 5, negative 2, negative 4. We have a root of 1, so that factor is x minus 1. So we'll put a 1 on the outside, bring down that first coefficient, multiply 1, add 6, multiply 6, add 4, multiply, we get 4, add, we get 0. And one more time, we are not surprised that we get a 0 as that remainder because we already knew that was a factor. Okay, 4 will be the constant, 6 will be the x coefficient, 1 will be the x squared coefficient. So we have the polynomial x squared plus 6x plus 4. Okay, think factors of 4 that add up to 6. This is not going to factor. Okay, so what we want to do here instead is we're going to have to use quadratic formula. Okay, we're going to have to use the quadratic formula. So, x squared plus 6x plus 4, set that equal to 0. Okay, since this won't factor, x squared plus 6x plus 4 is the final factor of this polynomial. And that's actually what part I want, so I could have written it down there. That's where that goes. Okay, so what we'll do instead is use the quadratic formula to solve this equation. Quadratic formula is something you probably need to memorize. It might be given to you a lot of places. It might not be. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. So as we plug that in, the a is 1, b is the 6, c is the 4. So x equals negative 6 plus or minus square root of 6 squared minus 4 times 1 times 4 all over 2 times 1. So then that gives us negative 6 plus or minus the square root of 20, 36 minus 16, all over 2. Square root of 20 can break up into square root of 4, square root of 5, 4 being a perfect square. So when we divide this out, or simplify that, we get negative 6 plus or minus 2 square root of 5 all over 2. Now, every single one of those coefficients can divide by 2. So we do need to simplify that one more time, divide everything by 2. So that's negative 3 plus or minus square root 5 all over 1, which we don't actually need. We divided out that 2. Okay? So we use the calculator and the table to find two nice roots. We factored those out. Okay, we factored those out. Then we had to use quadratic formula on the rest of this. Okay? Now, all of those solutions, x equals, we had a solution at double root at 0. We had a solution as single at 1. And we had 2 more that were not nice numbers, negative 3 plus and minus square root 5. These are your 5 solutions. Okay, that 0 was a double. And that plus or minus is 2 solutions. So there are 5 solutions here. Okay? Now, take a minute, graph this in the calculator. Graph the factored form, the one boxed in pink. Graph that in the calculator and make sure it matches what we started with. Now, if you do that, you'll see it really does work. So, one more problem. Let's look at example 5. We have an x to the 4th So we are expecting 4 solutions. Going to y equals, put that new equation in, and let's graph it. Now, looking at this, I see 2 solutions. We just said we were expecting 4. So something's up with those other 2 solutions. Okay, that root on the right really is a single root. It is not a big enough zigzag to count as a zigzag root. So it does go clean through the x-axis. So if we go to the table and see if we can find those roots, we have one of those roots at -1 because we have a 0 in that y column. We have another root at +1. Okay, those are the 2 real roots that we see, a -1 and a +1. Okay, so on this graph, we had a root at -1, we had a root at +1. Okay, we can actually see that y-intercept. It's going to be -5. And our graph went a little below that and then came back up through here. Now, that's not a great graph, but it gets the idea. It's a -1. Okay, total number of zeros here is going to be 4. There are 2 single zeros, no doubles, no triples. So that means there has to be 2 imaginaries in order to get us to 4 solutions total. So that does add up to our 4 solutions, and we want to find all of those zeros. So we do know so far that x equals, we have a -1 and a +1, and we'll have those 2 imaginary solutions. So to divide that out, we need to use synthetic division to divide those factors out. So 1, -4, 4, 4, -5. 1, -4, 4, 4, -5 are our coefficients. Okay, we know we have a root at x equals -1. So we know we have a factor of x plus 1. So we'll divide that out with a -1. Okay, drop that first coefficient down, multiply -1, add -5, multiply 5, add 9, multiply -9, add -5, multiply +5, 0. Now, we were expecting that remainder of 0 because we knew we had a root at x equals -1. Now, we also have a root at x equals +1. So divide out, disregard the 0, divide that factor of x minus 1 out by putting a +1 on the outside. Drop down that first coefficient, multiply, we get 1, add, we get -4, multiply to get -4, add to get the 5, multiply to get a 5, add, we get 0. And again, we are not surprised that we have a 0 in that remainder. Okay. Now, 0 is the remainder. There are no more factors to divide out. There's no more factors, no more real factors to divide out. That 0 was the remainder. 5 is the constant. -4 is x. 1 is x squared. So what that gives us as that next factor is x squared minus 4x plus 5. And if you're looking at that 4 and that 5 and thinking that will factor, let's try it. We would need a product of +5. We would need a sum of -4. The only way to get a product of a 5 is multiply 1 by 5. To get a +5, both signs have to be the same. Well, positive adds up to 6. If we use negative, that adds up to -6. Neither combination adds up to -4, so this won't actually factor. And if we think about it, we already sort of knew that because there were no other real roots on the graph. So there couldn't be any more factors that would lead to real solutions. So we take this final factor, x squared minus 4x plus 5. We set it equal to 0, and we need to use the quadratic formula to solve. So x would equal the negative of b is 4 plus or minus square root of -4 all squared minus 4 times 1 times 5 all over 2 times 1. Just plugging into the quadratic formula. So 4 plus or minus square root of 16 minus 20. Divide all that by 2. So 4 plus or minus the square root of -4 over 2. Now, that square root of -4, not what I wanted to do, that square root of -4 we need to work on. It's a negative, okay? It's a negative, so it's going to have an I. And when we take the square root of 4, we get 2. So this is 2 plus or minus 2i all divided by 2. Now, we do need to divide all of this by 2. So we get 1 plus or minus I. That is our pair of imaginary solutions. Those are our two complex solutions. So our final solutions, x equals, we had a root at -1, we had a root at +1, and we had a pair of imaginary roots at 1 plus or minus I. And that does count as two imaginary roots. So if we graph factored form, we will see that it does match the graph we had from the beginning. Here's our solution. Okay. So, quick recap. Take the equation, graph it in the calculator. Look for whole number roots and use synthetic division to divide those out. After you've divided those out, see if the remaining factor will factor more. If it won't, use quadratic formula to solve it. Also remember, the total number of solutions should always equal the degree of the polynomial. All right, y'all, that's it.